So the next speaker is Professor Markus Uhlmann. I hope I'm pronouncing your last name right.
Perfect, perfect.
Yes, he's a professor and a joint head of the institute and head of the CFD group at Karlsruhe Institute of Technology in Germany. He's also an associate editor of International Journal of Multiphase Flow and a member of the editorial board of Flow, Turbulence, and Combustion, and also in the steering committee of the Computer Center HLRS. His research interests are dynamics of coherent structures in turbulent flows, multiphase flows, numerical simulation techniques, and high performance computing. So I welcome you. The floor is yours.
Thank you very much for this kind introduction. So also thank you very much to the organizers for inviting me to this very nice event. What a better way to celebrate science and Bala's birthday. So happy birthday to you, Bala, once more. Many happy returns, and please keep on doing what you're doing. And thanks a lot for your contributions for the entire community, and also for your help personally and so on. Okay. So let me move on to the slides. Oops. There's of course some sharing button to be hit. I hope you can see this now. I changed the title slightly to make it a bit more readable. So our title is, Can Invariant Solutions Help Us to Investigate Particle Turbulence Interaction? Okay, so this is about bringing the two fields of particulate flow and dynamical systems approach to Navier-Stokes together. And I'm going to explain to you in the following what this means. This is work done by me and my colleagues at KIT, Tiago Pestana, Michael Kreyer, Xiao Binzu, and Konstantin Drach, and also collaborators from Osaka University, Genta Kawahara in particular. So the typical introduction is to show you a bit of motivation for attacking particulate flows in general, and we've already seen quite a lot in this meeting. Here are a few images from geophysics. As you know, the atmospheric boundary layer is full of hydrometeors, which are of interest, clouds, and so on. Sediment transport is done by rivers and other surface water bodies, which is an important phenomenon in shaping the Earth. You see, suspended sediment in form of plankton in the oceans. It's an important nutrient source. And then kind of natural contaminants in the atmospheric boundary layer due to, for example, volcanic eruptions. And of course, many more examples are coming from technical systems. So there's plenty of motivations, as you all know. And at the same time, although this is technologically relevant, there remain a lot of open questions, in particular with finite-size particles. So these pertain to the spatial distribution of particles. Clustering can essentially affect virtually all of the relevant quantities in a particulate flow system. Then how is the backcoupling of the particles on the carrier phase turbulence or the flow in general? And vice versa, what is turbulence doing to the particulate quantities of interest, such as settling velocity, collision frequency, dispersion, and many other quantities. So what we're typically doing, we are gathering data. So this might come from sophisticated experiments or from numerical simulation. And the big problem is, of course, that we have turbulence, which means this is a complex multi-scale process. And quite often, even if we have high quality data, it's not so easy to extract the physics out of this. Okay. So there are, of course, many approaches, and this can be done, but it's generally very tedious, involves all kinds of operations, and this is even worse if we add particles to the picture. Okay. So the idea is, and this is, of course, not a new idea, to simplify this problem a little bit, and hopefully we can advance our knowledge by perhaps boiling down the problem. So what have people done in the past? Considered simpler kind of proxy flows. Quite often this involves cellular vortices. This has been done already in the very early days in the 40s. And then, of course, in the seminal work by Maxey, where they or he considered Taylor-Green vortices and then looked at the influence on the particle settling velocity and evidenced phenomena such as preferential sweeping. This has also been realized experimentally, for example, in the group of Elisabeth. And with gravity. And yeah, you can also use other types of vortex models, if you like, or synthetic flows. For example, the group of Maybock has done this quite extensively, and so on. However, in a certain sense, one could say that many of these studies are somehow missing some features which are more close to turbulence, and that's the route which we want to go here. And it brings us to the dynamical systems approach to turbulence. So now we're completely shifting the perspective here. We're looking at Navier-Stokes, and we're not talking about particles so far. So you can consider Navier-Stokes as a system of ODEs. If you, for example, think about expanding in some basis functions like Fourier expansions, so you're discretizing in space, and then you have a system of ODEs with many degrees of freedom, where each degree of freedom is one of your variables, such as the Fourier coefficient or a grid point value. Okay, so Q is your vector of unknowns, which might be of very high dimensionality, perhaps 10 to the 5 or more. And then you can search for so-called invariant solutions, which might be of a simple equilibrium type, such that we have the time rate of change is 0. These are equilibria, or they could be relative equilibria, meaning that they are equilibria in some suitably chosen frame of reference. Or they might be so-called periodic orbits. That means that the solution repeats itself after some period capital T. Okay. So this is already actually not so easy to find, because this is a high dimensional system and these are nonlinear equations. So you have to do something similar to Newton iteration. In particular, you need a very good initial guess, otherwise you don't converge. And this is kind of like an art in itself. And there's a whole community doing this kind of work. And many of these invariant solutions have been found. And the good news from the dynamical point of view is that if you look at real turbulence, so the chaotic state, then the system is in state space wandering around these or some of these invariant solutions in time, sometimes approaching them very closely, spending some time in the vicinity of one or the other of these invariant solutions, and then getting spun away and approaching another one of these, a bit like a pinball system. Okay, and from that observation, you can then try to formulate a low order model by taking a handful of these invariant solutions and constructing a dynamical model, weighting each of them with the, let's say in a statistical sense, the probability of the full chaotic system approaching them over time. And this has been done, well, of course, first for toy models, but recently even for Navier-Stokes system. And this is an ongoing topic of research. So now let's take as one example Couette flow, which has arguably been investigated most in the fluid mechanics context, which is, well, just recalling flow between two parallel plates driven by the motion of the plates. You can actually go to channelflow.org, where there's extensive documentation of solutions and solution methods and even codes to download for searching for solutions. And here's just the phase space diagram in a very reduced dimension, just 2 dimensions, energy dissipation rate versus energy input or power input. And these gray dots show just some turbulent trajectory here. Each dot is a snapshot in time. And these colored, the dot is actually an equilibrium solution. One of the first ones which was found by Nagata at low Reynolds number. The red one is a periodic orbit. So this is a fully recurring solution, which just wanders around this orbit, nearly circular. And the blue one is another periodic orbit, a more complicated one, which is folding back on itself, but it's also wandering around here. These two were found by Kawahara and Kida, and these were the first ones which were found in the Couette system. Okay, so what do these solutions look like? Well, they feature essentially flow features which we are also seeing in turbulence, namely in this case, in one of these small cells, one pair of velocity streaks, high velocity in red, low velocity in blue, and these coherent quasi-streamwise vortices in green in between. Okay, so that's something that you can see in boundary layers in turbulence all the time. And the good news also is when you take just one of these solutions and you average over the wall parallel planes and you compare that to the statistical average of turbulence, you get a reasonably good match, at least for the low order statistics. So here this is showing the streamwise velocity fluctuations, or the Reynolds stress if you like. In the dashed line is the turbulence, and the colored lines are these invariant solutions. And this is for the wall normals. So you can see that's not a perfect match, but that is pretty good for such a simple solution. Okay, so one can say that the statistics of these invariant solutions at least some of them, are similar to turbulence. So basically taking a step back, so what are these invariant solutions? So they are simple recurrent flows or even equilibrium flows. They feature realistic coherent structures. They can be dynamically linked to turbulence in the sense that the dynamical system spends some time in the vicinity of them. These are not initial value problems, at least not for the carrier phase if we think about multiphase flow, right? So we don't need an initial value, or they don't depend on the initial value. They are reproducible, and potentially, if we now add particles to the picture, they would, at least that's the hope, to reduce the cost of our, let's say, parameter sweep campaign, right? So that's basically the scope of my talk here. Let's see what the potential is of this approach in the context of particulate flow. So let's stick with Couette flow for the beginning. So we want to track finite-sized particles in one of these solutions. And what we do first is to find a suitable parameter point. So we take this equilibrium solution by Nagata in some given box. And we track the solution as a function of the main parameter. Then the remaining three parameters, the Reynolds number, and you can see that you get these branches, upper and lower branch. And it was known before that there's a narrow region close to the onset of this existence of the solution where the solution is stable, and we choose one parameter point in the stable region. This is done in spectral space, which is more efficient. And then we take our immersed boundary solver, which is using kind of a classic method, but that's not, you could use any kind of particle resolved DNS method. And we are inserting particles. So initially we're setting the particles in balance with the fluid flow at the same position, and we're setting the angular velocity of the particles to 0. So we are here investigating horizontal Couette flow, meaning that gravity is directed perpendicular to the plate. And we're adding a single particle for starters. And we can see that, of course, this depends on the choice of the particle parameters. This is a particle which has a diameter to height ratio of 0.156. So h is the half width, and a certain Galileo number and density. And we can see that the solution is essentially maintained. So here what we're seeing is the perturbation of the turbulent kinetic energy after we insert the particle. And we can see from the scale here, this is very small. It attains nearly steady state. If we zoom in, this is actually oscillating at a very tiny amplitude. And so strictly speaking, we have not found, or we have not maintained the equilibrium solution, but we have found like a very tiny periodicity in the solution once we add the particle. So once we have established this stability, if you like, with the particle, we can systematically explore the parameter space. What we still have to do is to more systematically check the stability with varying the particle parameters. So next question is, where do the particles go in the flow? And we see the familiar dynamics here. We insert the particle somewhere in the domain, and after several recurrences around the periodic direction, it will end up in a low speed streak. Okay, so I have to mention that these particles are heavy in the sense that they are constrained to the vicinity of the bottom plate. Okay, so they migrate to the low speed streak, similar to what is found in turbulence and experiments many times. So here you see a snapshot from a DNS by Kidana, Mariam, and others at much higher Reynolds number. You compare factor 10 higher, where we have already found, and others as well, that particles even dynamically and in fully turbulent flow go into the low speed streaks. And one manifestation of that is that the apparent velocity lag, which you can compute by, let's say, naively averaging the phases separately over the plane, is of the order of the wall shear stress. The wall shear velocity, which is essentially a measure for the intensity of the streaks. Okay, so there's a nice match between these two phenomena, at least qualitatively. We have also looked a little bit at the density ratio. We have also looked at different initial conditions and whether this works with multiple particles. So far we were looking at equilibrium solutions, so there were no, let's say, dynamics of the single phase Navier-Stokes solution. The question is, can we also work with periodic solutions, so periodic orbits? And actually it turns out that the Kawahara-Kida gentle periodic orbit is robust. Robust meaning it's maintained well even when we add these kind of particles. And once we have established that, we can start studying things We can, for example, look at particle resuspension dynamics or the dynamics of particles which are already in suspension. So here we're taking, so on the left here, we are looking at the time evolution of the average wall normal distance, average over particle sets as a function of time for different Galileo numbers, keeping fixed the particle size in wall units and the density. Okay, so you can see that very light particles, of course, get entrained quickly and then do their thing. And more heavy particles will be grounded close to the wall. And this way, by varying systematically Galileo, you find a critical Galileo number for resuspension. And you can also look at the dynamics in the cross-section. You can already see from these a bit chaotic plots that the particles avoid these large-scale vortices here. Now going to the critical Galileo number, you can do this for all kinds of particle classes. So here we have a diagram of critical wall shear. So this is essentially a Shields number versus the particle size in wall units. And the different symbol colors are the different solutions we have used to establish this diagram. So you can see the equilibrium solution in yellowish. You can see the gentle periodic orbit in red and the vigorous periodic orbit in blue. And you can then start completing this diagram. And what we found so far, but this is preliminary data, is that these different solutions give at least what we could call consistent results. Okay, so they exhibit similar dynamics and they're similar to turbulence, which is the gray dots here. Okay. So next, I would also like to give you a glimpse on another configuration, which is open channel flow. So why are we interested in open channel flow? Here you can see the setup which we're looking at in fully turbulent simulations first. So there's a sediment bed and there's a free surface here and there's a turbulent flow driven over the sediment bed. And we're bringing in some contaminant particles. So this would be interesting in studies of contamination, how this settles and disperses and then moves into the bed here. Okay, so we are deliberately choosing relatively short domains here in order to suppress the formation of patterns on the bottom, which is another topic, but I'm not going to show this today. So these are relatively short domains. The Reynolds number is intermediate, but also relatively high. There are different sets. And we're looking at contamination or contaminant particles in a certain parameter range. Okay. So what do these DNS show? So we're not yet at the point of invariant solutions. They come next, but the DNS of the fully turbulent situation show actually quite an important effect on the mean settling velocity of turbulence, depending on the particle parameters. So you can have very strongly or much higher settling velocities or peak settling velocities than in still air, which is 1 here, or -1, sorry. So you can have more than 50% increase of settling velocity depending on the particle parameters. You can parameterize in a sense here in Galileo number, but we get to that in a second. And this is essentially due to preferential sweeping. So here there's a cross section. This is the streamwise averaged wall normal velocity. So the red is upward flow and the blue is downward flow. And you can see, well, in this plane, it's all the particles through the domain collapsed. That particles are essentially going downwards in the blue regions. So that means, at least for this parameter point, that there's enhanced settling. This is also visible in wall parallel planes in the bulk, where you can see that particles are essentially concentrated in the blue regions. Okay. So now we get back to the invariant solutions. So again, this is our turbulent system. And there's a few solutions available which have the correct, let's say, boundary conditions, so consistent with open channel flow. One is the solution by Wolef. It's a, let's say, classical wavy streak solution. And then there's also a more recent solution by Shecker and Graham, which is interesting because it can be tracked also to higher Reynolds number, and it also features a hairpin-like structure with span-wise vorticity. So what we've done is we have chosen this, that's what actually Michael Kreyer has done. He has chosen this Shecker and Graham solution. And he has swept quite closely the initial condition space. So he has put particles on the top using also the fourfold symmetries of the system. So each parameter point is swept by 288 in the different initial particle positions. Okay, so I have to mention that these solutions are slightly slowly unstable, but we monitor the difference with respect to the single phase solutions. So we are okay for, let's say, order 10 to 100 bulk time units. Okay. So here are the results from the campaign with this invariant solution type. again, here we have the mean settling speed over these particle sets, comparing fully turbulent in dashed with the traveling wave solution or the invariant solution. So in the turbulent, this is statistical averaging, even over several realizations, whereas in the traveling wave, these are just different initial conditions on a single solution. And you could say that the match is quite remarkable. We get the good trend with Galileo for the settling velocity here, and even the time evolution is relatively closely matched. Okay, so we can say that this is very well captured with this relatively simple solution at much lower Reynolds number. Okay, so now the good thing is that using these invariant solutions, we can do a very extensive parameter sweep. Okay, so here one of these runs is already these 288 initial conditions, but now we can vary also the particle parameter points relatively easily. It's still relatively painful, but each run is at least quite cheap. So this diagram sums up this campaign. So each of these small dots here is one parameter point. And we have varied, or Michael has varied actually the Galileo number, as I said, and also the density ratio. So this plot shows the peak settling velocity. So everything above 1 is an increase, everything below 1 is a decrease or reduction in settling velocity. And parametrized as a function of the turbulence intensity, or relative turbulence intensity, shown by, wall shear velocity versus terminal settling velocity. And you can see that this more or less collapses the data quite well. And these black dots are the few data points which we have from the fully turbulent DNS, which is also quite consistent with the traveling wave data. Okay, so we could speak of an approximate collapse with the relative turbulence intensity and an extensive parameter sweep using the traveling wave solutions. Okay, so to sum this up, the invariant solution approach, as far as we have investigated it up to today, actually is quite promising. So first of all, we have found stable solutions with finite-size particles, which is already an interesting result as such, because it might help investigating the transition scenario. Then we have also found that even if the solution is mildly unstable, then these solutions are helpful for us, and we can still use them, at least over a certain observation interval. Then the particle dynamics exhibit realistic features. They show migration to low speed streaks. They also can replicate the settling velocity enhancement in open channel flow, and probably in the future other things. So now I think the road is, or the avenue is open for exploring additional configurations, performing more extensive parametric sweeps, and then hopefully address these open questions. So other configurations which we can tackle are, of course, unbounded flows, so triply periodic situations, then other wall-bounded shear flows like pipe flow and so on, all of those for which invariant solutions have been found by the dynamical systems community. But also thermal convection systems are good candidates to investigate in the future. There's another perspective which is very nice, I think, is to investigate point particles in invariant solutions. As far as I know, this has not been done. And this really leads to very, very efficient and very fast computation, because in particular, if point particles are one-way coupled, you can essentially load these solutions into memory and then track the particle through these, track a huge cloud of particles through these solutions. Okay. So let me just leave you with perspective here. We have also started looking at unbounded systems, and the one which we have targeted a little bit is homogeneous flow with 2D Taylor-Green forcing. So this is basically starting with 2D Taylor-Green, but going one step further. And you can find either quasi-periodic or truly periodic solutions, and even some stable ones, which exhibit this kind of dynamics here. If we look at them, so the cycle goes from left to right. You have essentially the Taylor-Green vortex columns, but they're slightly perturbed in a helical way. And over the cycle, there's a secondary vorticity being formed in the plane perpendicular to that in the form of these green cigar-like vortices, which then again disappears, and then the cycle comes back. Okay, and then you can go and investigate the stability of these solutions by adding particles, and you can approximately collapse this by using the mass loading. and then investigate hopefully many interesting things such as the dispersion in the cross plane and other things. Okay, so with that, I'm at the end of my talk. I thank all the sponsors and people who have helped to track down these solutions in the different systems, and I'm ready to take your questions.
Thank you, Professor Uhlmann. Very exciting presentation. We have room for a few questions from the audience. Okay. I have a question regarding the solver for the DNS solver part. There was this sand bed on the that you showed, like the particles in an open channel flow, and there was a sand bed. But the sand bed was also modeled using a point particle method, or is it just a corrugated surface using a mesh boundary? Or
can you see my slide still?
Yes.
Okay, so you mean this one? There is no, well, actually, all the particles are fully mobile and fully resolved. So this is actually a much more complex simulation where we are also tackling scalar transfer and other things. So you're right, in a sense, for this particular study, we could have done with the DNS without this bed. Probably the thing is that the moving bed, even if it's featureless, it's porous and there's a moving particle layer and there's some small roughness, or not that small, actually transitionally rough. So this sets a higher friction Reynolds number. Okay, so this sets a higher shear stress, but for the flow on top of it, that's about it. Okay, but you're right, we could have done it without it, at least for this part of the study, but we were also investigating other things.
Yes, thank you. Any other questions from the audience? There's one question in the chat box, I think.
Okay.
From Zen Lee, it says, for the full resolved DNS simulation, will the charges on the particles affect the flow field evolution?
The charges?
Charges on the particles.
I don't know. Depends on the charges. I mean, if you would charge the particles, I guess yes, yeah. We didn't look at that.
Ragesh, Yali Tang has a question.
Oh, okay.
She has her hands up.
Yeah. Oh, okay. Yeah, sorry, I didn't see that. Oh, yeah, sure. Go ahead.
Just very short question. And by the way, thanks to Markus for a very nice presentation. And in the outlook, you're pointing out some future research, but I was wondering, how about the particle shape? Do you consider that also in the picture, the whole picture of the topic? Because I assume that currently all the particles are spherical, right?
Yes, I mean, you're absolutely right. Of course, one can change the particle shape, and computationally, I don't see any problem there. The thing is, we already have so much to do. The parameter space is already quite big, and we haven't even touched the tip of the iceberg. But yes, it can be easily listed. I mean, it can be truly added to the list. You're right.
Yeah, indeed. Yeah. Okay. Thank you.
Thanks.
Okay.
Markus. Yeah. Markus, I have a question. It's really fascinating work. It's amazing that these reduced order solutions, what you have shown is that they replicate not just the shear stress and other statistics, but they also reproduce particle dynamics within them, so that you don't have to do very expensive turbulence simulations. You could do much cheaper solutions and recover quantities such as mean settling velocity and so on and so forth. You can say whether my understanding is correct, but the real question is that if this is the one-way coupled effect, when you allow two-way coupling, even the steady state that you're shown may change. Has someone looked at that?
By steady state, you mean whether the equilibrium solution is maintained?
Equilibrium, yeah. Fixed point solutions or limit cycle solutions will change as you give two-way coupling. That problem is also interesting. But the problem that you showed in the one-way coupled regime, it allows you to explore the parametric space extensively.
But our simulations are fully two-way coupled. I mean, what I showed was everything was two-way coupled. I mean, only my perspective was one way. Basically, we jumped one step ahead and we did the fully two-way coupled with finite-sized particles. So that's the whole talk. But at the end, actually, after a while, we realized, hey, we could have done point particles first. So no one has done point particles as far as I know.
So
but this is really, I mean, this is really, really cheap.
So if you one does the point particle with the simpler flow, they could even explore even more extensively, because this question of
turbo
whether
phoresis, for example.
Thank you.